We're going to turn our attention now to light, um, and we're going to start by thinking of it as light as rays moving through the air, and later we'll do waves. So, but right now, sticking with rays.
Um, so we're going to start with this idea that's sometimes called the wave-particle duality, and that is that light can be described both as a wave and as a ray. So on the one hand, it's easy for us to think of what light traveling in a straight line. So if we look at this laser, this cool picture of a laser shooting up into the sky, uh, or a flashlight. We direct light all the time in a particular direction, and so we think of it as moving from one place to another in a straight line. Uh, but also, we know that that light is a wave, so it's one of a number of different kinds of electromagnetic waves. So that's what that EM means. There are a lot of different kinds of EM waves, X-rays, microwaves, gamma rays, all sorts of stuff. And visible light is just a small part of that spectrum. But it is a wave. And so light does have a physical basis for both of these ways of seeing it. One is if we think of it as traveling photons, which are little particles of electromagnetic energy. We have evidence that photons exist, right? And we think of particles as traveling in a straight line, and so it makes perfect sense that we would think of light as a ray. It's just the particles moving from one place to another in a straight line. On the other hand, we also know that light is an electromagnetic wave. It has a frequency, a wavelength, an amplitude, and so forth. And so it's definitely a wave as well. And this is actually one of the great mysteries of physics. I mean, we can describe light as a ray, we can describe light as a wave, but when you get down to it and you say, well, what is light? Is it a wave or a particle? We don't really have a good answer to that question. Our metaphors sort of fall apart, and we'll get into some of the interesting ways that shows up. But keep that in mind. Both of these are they do have a physical basis, but they're limited. They don't fully, neither the wave nor the ray um, idea fully captures what's going on with light. Okay, so when do we use each of these different models? The general rule is that when an electromagnetic wave interacts with an object bigger than its wavelength, we're going to think of it as traveling as a particle or as a ray. Okay, what's a wavelength of visible light? Very small. Okay, so in almost all sort of ordinary everyday situations, um, the ray model for light is going to work pretty well for us. And maybe the best reason, um, our best example of that is when we think of a shadow, right? So here we have the sun shining past two people who are dearly in love in some beautiful old European city. And so the light, either travels past them and hits the pavement, or it hits their body and then no light hits the pavement here. Okay, that's thinking of light as a ray. It travels in a straight line from the sun and it goes to one place. It either passes them by and hits the road, or it hits the body and stops there. Um, so in a lot of everyday situations, that's going to be our model. The study of light as a ray is called geometric optics, and so that's going to be the topic of our upcoming lectures. So the first law, there are two laws that govern geometric optics. One is the law of reflection, which we'll deal with today, and the other is the law of refraction, which we'll get to next time. The law of reflection is really quite simple, and I think it's pretty intuitive too. If light bounces off a surface, the angle of reflection is equal to the angle of incidence. So what do those terms mean? The angle of incidence is incident light means it's hitting a surface, right? So it's coming into the surface. And we always measure the angle from the normal of the surface. That is the perpendicular the axis that is perpendicular to the surface. So if that angle is equal to theta incident, right, the reflected ray has the same angle theta reflected. And so these two angles here are equal, and it reflects in the way that we would expect something that was going in a straight line would reflect. Now, that gets a little confusing when you look at a light hitting, say, a rough surface, right, where you don't see a perfect reflection. And what you'd have to do is look at a kind of microscopic picture of that surface, right? So even say that a tabletop, if we look at it microscopically, is going to have lots of these little hills and valleys. And so light is going to come in here, and at each given point, we're going to find a normal to the surface, and that law of reflection is going to be true, right? So the law of reflection is true here, and it bounces off this way. This one, we have a surface that's sort of slanted this way, and so the law of refraction is still true, but it means the ray bounces off this way. So this is why a mirror works well, right? A mirror has to be, is basically a surface in which you try and get rid of as many of these hills and valleys as possible, and that gives you a nice clean reflection. But if you have a surface that is more rough, like a tabletop, your reflection is going to be a lot more diffuse, and so you're not going to get this perfect image of whatever is being reflected by the surface. So that's the law of reflection.